Okay, welcome students for the GATE coaching class for today's sessions. Myself T.SATHIsh working as a assistant professor in the Department of Electrical and Electronics Engineering, S.A.E.C Engineering College. Today we are going to see the GATE coaching on simple diode circuits. In that, applications, clipper, clamper and rectifiers. We are going to discuss the topics on a diode based on the applications of your diode, clipper circuits, clamper circuits as well as rectifiers, and also we are going to discuss what are the problems we are going to be discussed in clipper, clamper as well as rectifier in GATE questions, previous year's questions what they asked, that we are going to discuss in today's sessions. Okay, what about your diode? There are the different types of semiconductor materials we are going to use. One is your silicon semiconductor material, another one is going to be a germanium semiconductor material. Most probably for forming the PN junction diode we are going to use your silicon semiconductor materials. Okay, one is going to be called as your N-type material, another one is going to be your P-type material. For N-type material we are going to use your pentavalent material to be doped in your semiconductor material. For P-type materials we are going to dope your trivalent materials for forming your P-type materials. Together we are going to form the PN junction diodes. One is going to be a P-type material, another one is going to be a N-type material. The combinations of both P and N gives your diode. Okay, this is the one of the semiconductor material which is used in your semiconductor device in your electronic circuits. Okay, this PN junction diodes is going to be used for switching applications. It's going to be used for switching applications. Okay, these are the block diagram symbols, the representation of your PN junction diodes. Okay, one terminal we are going to be called as the anode terminal, another terminal we are going to be called as your cathode terminals, where we are going to give your voltage source. According to that, it's going to be operated. Main thing we have to discuss about the characteristics of a PN junction diodes. Okay, the diode going to be operated in a positive cycle as well as a negative cycles. If you are applying a voltage source, AC voltage source, when you are applying a voltage source, there are the positive cycle as well as the negative cycles. During positive cycle, diode is going to be conducted in forward bias conditions. Okay, this is going to be a forward bias conditions. During your negative cycles, a diode is going to be conducted in your reverse bias conditions. When the applied voltage reaches your forward knee voltages, 0.7 volt for your silicon material, 0.3 volt for your germanium material. When the applied voltage reaches your 0.7 volt, a diode start conducting. Once diode start conducting, there will be a gradual increase in your current. That time your diode is in on conditions. There will be a conductions of your diode and there will be a flow of electrons from one regions to the another regions. When the cycle reaches your negative cycles, okay, it is in reverse bias conditions. That time only a very few amount of current only flows in your diode. Once the voltage reaches in reverse directions, when it reaches the breakdown voltage, the current start increasing rapidly. This is the VA characteristics of your PN junction diode. During your reverse bias conditions, a diode is off condition. These are the VA characteristics of PN junction diodes. And next one is going to be the Zener diode. The Zener diode is most important thing is it is a highly doped semiconductor device. Especially it is going to be operated in your reverse directions. It is main thing is going to be highly doped semiconductor device which is specially designed for the function in reverse directions. The major applications of your Zener diode is going to be worked as a voltage regulator. It's going to be provide constant voltage value. So that we are going to use your Zener diode. The Zener diode is only the applications is going to be operated in your reverse bias conditions. Here they are going to be a same terminal as going to be a p-type material as well as the n-type material, same anode as well as the cathode. The symbol is going to be the differ with your p-n junction diodes. Okay, the major advantage of the p-n junction diode as well as your Zener diode is going to be the switching operations. For your Zener diode, it's going to be operated for your constant voltage source. And next major thing is going to be the applications of p-n junction diodes where we can use it. The first application is going to be your rectifiers. We're going to be used as a rectifiers, and next applications we're going to be used as a clipper as well as your clamper circuits where diode can be used. Okay, if it is a rectifiers, we're going to convert your DC AC to DC voltages. We're going to apply your AC input and we're going to be converted to your DC output, acquired output. For that we can use your device, semiconductor device, diode. We're going to be using for conversion of your AC supply to the DC supply. There are different types of rectifiers are there. One is going to be the half-wave rectifiers, another one is going to be the full-wave rectifiers, and third method is going to be the bridge rectifiers. There are three different types of rectifiers are there, which is going to give the same output. We're going to apply your AC input as well as your we're going to get output as a DC. What the difference between these three type of rectifier is, one is only one diode is going to be used for your half-wave rectifiers. For full-wave rectifiers we are going to use your two diodes, diode D1 as well as your diode D2. Whereas in bridge rectifiers we are going to use four diodes. Whereas in bridge rectifiers we are going to use your four diodes. In that, diode D1 and D2 will be in forward bias conditions, and diode D3 and D4 will be in reverse bias conditions. Okay, whereas in your full wave rectifiers there are two diode D1 and D2. During the positive cycle, diode D1 will be in forward bias conditions. Okay, during negative cycles the diode D2 will be in forward bias conditions. Okay, so this for both cycle, positive as well as negative cycle, your full wave rectifier is going to be operated and it's going to convert your AC signal to the DC. But in case of your half wave rectifiers, a diode we have only a one diode which is going to be conduct only for the positive cycle. During negative cycle, a diode will be in off conditions. Okay, so we can convert your output like this. This is your input and your output is going to be only a pulsating DC. During positive cycles only your diode will be in on conditions. For negative cycle, diode will be in off conditions. This is in case of your half-wave rectifiers. Next, in case of full-wave rectifiers. Full-wave rectifiers, we are applying a AC voltage source. Okay, in full wave rectifier as well as a bridge rectifier, the output is going to be the same. The output is going to be your positive, again positive, positive, positive. So that here a diode D1 is in forward bias. Here diode D2 will be in forward bias. So during your input cycles, for positive flow there will be a diode D1 will be conducting. For negative cycles, a diode D2 will be in conducting. So you're going to convert your AC input to your DC input. But here it is not a pure DC, it is a pulsating DC. When you go for your bridge rectifiers, okay, the same output as we got for your half-wave rectifiers, but only the difference is during positive cycle diode D1, D2 is in forward bias. Two diode is going to be conducting during the positive cycle. For negative cycle, diode D3 as well as your D4 will be in forward bias. The remaining time your diode D1, D2 will goes to reverse bias conditions. So this is your input as well as the output of your rectifiers. The applications of a Zener diode we are using in your rectifier circuits, that it's going to convert your AC signal to the DC signals. Okay, here it is not a pure DC. For getting a pure DC, we have to add your filter circuits so that we can convert these rectifiers to the pure DC. So once we apply your filter circuits in your rectifiers, so the pulsating DC can be converted to your pure DC. And next application is going to be the diode application is going to be the clipper as well as your clamper circuits. This is your clipper circuit. This is your clamper circuits. What is the difference between the clipper and clamper? Clipper means if your input signal is your AC signals, if you want to remove any portions in that waveforms, we can remove that signals. Here it is, I have removed the positive signals. Okay, so if you want to remove your negative signals, also we are able to remove your negative signals based upon the connections of your diodes. Okay, in clipper there are diodes will be connected either in series connected or it may be in parallel connected, because there are many types of your clipper circuits. Okay, here it is connected in series. The same thing, the diode can be connected in parallel also, so that your diode can be named as parallel clipper as well as your series clipper. The diagram which I have shown is your series clipper. In that there are different methods are there. When you apply your positive voltages, now this is your anode, this is your cathode is given, this is your anode terminal. If I give your negative sign here, then it will be forward bias, so it is your negative clipper. If I give a positive sign, then I have to interchange this diode so that it can be called as a positive clipper, negative clipper. With biasing as well as the without biasing is the concept. If I apply a voltage source here, then it's going to be a biasing clipper, so that the unwanted portions in your waveforms we can be removed. If it is your input cycle is your AC, output is going to be a clip. If you want, I can clip the. If I want, I can clip this signal also. I can clip this part. It is also be applicable only we are applying a DC voltage source. Bias we have to apply so that the unwanted portions in that particular waveform, so either in positive cycle or it may be in negative cycles, we can remove. For that purpose we can use a clipper. Okay, this is the one of the applications where we have to remove the unwanted signals or unwanted portions, unwanted waveforms. There we can use your clipper circuits by using your diode. And next application is going to be your clamper. The advantage of the clamper circuit is going to, we can shift the entire signal from the negative cycles to the positive or positive cycle to the negative cycles. Okay, our input is going to be your purely AC wave where it have your positive sign and also have your negative sign, positive as well as your negatives. It's going to be conduct for both the positive 0 to pi is going to be the positive cycle and pi to 2 pi is going to be the negative cycles. But in case for my applications, I no need of any negative signals, but I need your entire signal to be shifted from your downward to the upward movement or upward to the downward. If it is upward means it is a positive, downward means it is a negative. You can see this waveform, the entire negative cycles, is shifted to the positive. Okay, now I can say this is your positive clamper circuits. Okay, if I need to connect your negative clamper, so this diode can be interchanged like this. I can change like this, so this can be your negative clipper. So my waveforms will be like this. The entire cycles will be shifted to your negative sign. So your positive sign is clamped. Positive sign is clamped and it is shifted to the negatives. But in case of your positive clamper, the negative sign is clamped and it is moved to your positive side. This is the some applications where we can use your clamper. So the application of your PN junction diode is going to be your rectifier circuits, as well as for your half wave rectifier, full wave rectifier, bridge rectifiers. The diode can be also used in your clipper circuit as well as your clamper circuit. These are the applications where we can use your diodes. Based upon these applications, now we are going to discuss some previous year gate questions. Okay, first problem. The problem number 1, which is asked in the problem number 1, which is asked in here 2022 gate questions. Okay, it is asked in previous year gate questions. It is simple that from the circuit shown below with the ideal diodes. If ideal means both the diode have the same configurations, there is no difference in that. What is will be the output? They are given 4 options. The output voltage is equal to input voltage for V in is greater than 0, first option. Second option, the output voltage is equal to input voltage for V in is less than 0. Here it is less than, here it is greater than. And third option is given as the output voltage V out is equal to minus V in for greater than 0 and minus V in for less than 0. It is option D. We have to choose which answer is a right answer. You know that when the diode conducts, it should be in forward bias. When it is not conduct, it is in reverse bias. Then it should be in open circuits. Now you can say your AC sign is applying. Now you are applying your AC input when during your positive cycle. During your positive cycles, your diode is in on condition. So it is in forward bias condition. So the current flows in this direction, okay, and the flows through the load resistance. Okay, when enters into the diode D2, again because this is your anode, this is your cathode. So diode is going to be in on conditions and it's going to be forward bias. So the flow of current should be like this. So the input current, input voltage what we are applying is positive cycle. So both the diode is going to be in on conditions. During that time a diode is in closed switch. It has going to be act as a switch, so it is closed. So the entire current is going to be flows in these circuits. The entire current is going to be the flows in the circuits. So input voltage what we are applying is equal to your output voltage. Okay, because there is a closed loop circuits, so there will be a option A as well as your option B is right, because your output voltage is equal to input voltage, because both the diode is in forward bias, it is in on condition, so switch is closed, so there will be a closed loop. So the current is flowing through the diode D1, a resistor R1 as well as a resistor R2. So the first 2 option is going to be the right option. In that, which one is going to be the correct option, we are going to find next one. Okay, here you can see it is greater than 0 or less than 0. Maybe option A or B is going to be the right. In that, which one we are going to find is when your input voltage is greater than 0, it means that the applied voltage when it reaches to maximum. Okay, the diode operation is going to be when the applied voltage reaches your 0.7 volt, then only diode start conducting. We know that when it reaches your knee voltages or threshold voltages of 0.7 for your silicon material, a diode will be in on conditions. That time we can say your input voltage V should be greater than 0, then only your diode will be in conducting. So the option A, V out is equal to V in for V in is greater than 0 is your right answer. And also you can check with your second one, it is less than 0. If it is less than 0, we are not applying your input voltages. Less than 0, it is a negative voltages. If it is a negative voltages, your diode will be in reverse bias condition, so it is going to be in open circuit. If it is open circuit, there is no flow of current, so we can't say output voltage is equal to input voltage. So the correct option is going to be your V out is equal to V in for input voltage greater than 0. This is your right option. This is your problem number 1. It is asked in your previous year guest question. And second problem, this is a problem number 2. It is also asked in your previous year 2023 gate questions, diodes and its applications. It asked, okay, here in this circuit shown below, the knee current of the Zener diode is given as 10 milliamps. Okay, a knee current. Okay, so knee current values of your Zener diode is given as 10 milliamps. The current flows through the Zener diode. It is given. IZ is given. Okay, to maintain the 5 volt across RL. RL represents your load resistance. Okay, it's a RL load resistance. It's not inductance. It is a load resistance. Okay, across that we are maintaining the voltage of 5 volt. Okay, and the minimum value of the RL in ohms. We have to find the load resistance. This is your load resistance. Load resistance. We're going to find the load resistance in terms of ohm. So that we're going to find your RL. What is the value of your RL for these circuits? And the minimum power rating of the Zener diode in milliwatts. Okay, it's going to be find your power rating. Okay, sorry. We're going to find RL as well as your Zener power. These two things we're going to be calculate in this problem. For that they are given 125 ohms. This is your milliwatt. It is given. In these 4 options, which one we going to be right answer? We can execute. Okay, you can see this is your input. Yeah, the input voltage is going to be the 5 volt. It is given in your problem. And next, your series resistor 100 ohms is given in your problem. This is your series resistor is connected in your circuit, so it is going to be the 100 ohms. And Zener voltage VZ is given here. So VZ is given here. Okay, Zener voltage is going to be the 5 volt. And new voltages, okay, where the current is flowing in your Zener is going to be your 100 milliampere. It is given. This is all the given data. Okay, main thing across the load resistance RL. Okay, we want to maintain your 5 volt. Okay, in this load resistance we have to maintain your 5 volt. Then we need to find what is the value of your load resistance when we are maintaining your 5 volt across your Zener diodes. Okay, for first step we have to calculate the total current through the 100 ohm resistance. If it is a 100 ohm resistance, what is the current flowing here? That is your I total current which is going to be flows in 100 ohm resistor, so that we can calculate the what is the current flowing in your load resistance also. For that we can use the formula, the voltage drop across, okay, across the 100 ohm resistor. We are going to find the voltage across this. What is the voltage? So resistance voltage is equal to V in minus your Vz. Okay, we know that total voltage is going to be a V in is equal to 10 volt. It is given, and a Zener voltage is given as 5 volt. So that we can find the value of the voltage across the resistance is equal to 5 volt. Reason is here it is the 5 volt it is given. So the total voltage is 10 volt. So we can find the remaining voltage of your resistance. That is going to be your 5 volt resistance. Okay, and next, so the total current through the resistor. Okay, so we have calculated your voltage, so that we can find the value of your resistance as well as your current. Your total current I total is equal to VR divided by series resistance. This is going to be your series resistance. Your VR voltage is your voltage across your resistance is given as 5. Okay, voltage what we have calculated here is going to be the 5 volt across your resistor divided by your load resistance is going to be the 100. So we are going to get 0.05 amps or 50 milliamps. That is the total current. Here the total current which is flowing is I total is equal to 50 milliamps current is flowing from the voltage source through your 100 ohm resistor. So now we know that here the current is going to be your, this current is going to be your 50 milliamps. Here the flow of current is going to be the 10 milliamps. What is the current flowing here? It is the load current. We are going to calculate next. Okay, what is the load current which is going to be flows in your load resistance? Okay, we know that the zener must be a breakdown which have a zener knee current as 10 milliamperes. The maximum current, okay, the maximum input current, the load current it is going to find. See, so the total load current minus your zener current. The sum of the current entering here is equal to sum of the current leaving according to your Kirchhoff law. We can write. So 50 milliamps minus your 10 milliamps. This is your total current, and this is your zener minimum current. So that 40 milliamps of current is going to be flows in your load resistance. Here is going to be the 40 milliamps current. And next we have the flow of current as well as your voltage across your load resistance. According to that we can find the value of your load resistance. So the formula for finding a load resistance R is equal to V by I. So zener voltage, the zener voltage is going to be connected in parallel with your load resistance. So we can take your zener voltage divided by your load current, what we have calculated right now, which is equal to 5 divided by 0.04 is a milliamps. So we can have 125 ohms is your load resistance. Here 125 ohms is your load resistance. Okay, in this we have find the load resistance value as 1.5. Yes, the load resistance value is 1.5 we have calculated. So maybe there will be two options, will be right options. One is going to be option A, another is going to be the option B. This is 125. And next we have to calculate the power values. Next we have to calculate the power values. How we can calculate the power? Power I is equal to and V and P. P is equal to, we know that I square R is your formula for calculating the power. Okay, what is the current flows through your load resistance? Okay, what is the power flows through the zener diode is going to be a 0.01 square into load resistance. What we have calculated here is going to be 125 ohms. So 125. So answer is going to be again 125 millivolt is the power across your zener diode. So the option is going to be your first options. This is going to be the millivolt. First option is going to be the right answer. This is your right answer. And next one, next problem, third problem. Okay, here it is also going to be a zener diode problems, but one thing is here it is connected with your transistor. Okay, here it is connected with the transistor as well as your zener diodes. Here we are going to calculate the current flows through the 20 ohm resistor. What is the current which is going to be flows in your 20 ohm resistor? We are going to be calculated. Here it is given that, okay, here it is given that the beta value is going to be a 99, okay, and the voltage, a breakdown voltage of your zener diode it is given. If it is a breakdown voltage, we know that the diode is in off conditions. So the diode is going to be in off. We're going to consider the main thing. We're going to find the current through 20 ohm resistors, okay, in milliamperes. Okay, first thing we're going to assume that a zener diode is going to be in off conditions. Our zener diode is in off conditions. Reason is it is in breakdown region, so we are open the zener diode. Zener diode we have open because it is in reverse bias breakdown condition, so we have opened. So the flow of current is going to be a 25 volt 7k kilo ohm resistor through the transistor, and next it will be move on to your 10 ohm resistor, then it will be move on to your 20 ohm resistors, and it will be back to the source. There will be, this is the flow of current for a given circuits. This is the flow of current. How we can calculate your current through the 20 ohm resistance? We are going to find your IE, what is the current which are flowing. Okay, according to the Kirchhoff law, we can have a statement that 7 kilo ohms into current IB. There will be a flow of current in 7 kilo ohms into IB plus the current which enter into your transistors, then it will be entering into your 10 ohm resistor into your emitter current, plus again your current is going to be flows in your 20 ohm resistor with emitter current, which is equal to your voltage 25 volt. These are the equations according to Kirchhoff law we can write. Here we can do your simplifications. 7k IB, it's a base current, plus here we can write this is a 10 ohms emitter current plus 20 ohms emitter current, so total 30 ohms emitter current is equal to 25 volt. Here you can see it is a base current as well as a emitter current, so we can convert this ohm IB plus this 30 as it is, 30 ohms as it is. We can convert your emitter current in terms of beta plus 1 of IB. So the above equations can be changes to in terms of base current, which is equal to 20 volt. Next step, the final equations what we have written is 7k IB plus 30 ohms beta plus 1 into IB equal to 25 volt. And next, this as it is 7k IB plus 30 as it is 30 ohms. The beta value here it is given as 99 plus 1. So 99 plus 1 into IB is equal to 25. And next, here we can convert to 7000. Here it is the kilo ohms. So I am converting to 7000. So IB plus 30 into this 30 into 100. 99 plus 100. So it is going to be a 3000 IB, which is equal to 25. So 10,000 IB equal to 25. So the base current IB is equal to 25 divided by 10,000, which is equal to, we are going to get 2.5 milliamps. The base current what we have calculated IB is equal to 2.5 milliamps. But in your 20 ohm resistor, there will be a flow of emitter current. So we have to find the emitter current. IE is equal to beta plus 1 into IB. So we know that 99 plus 1 into 2.5. So 250 milliamps is your emitter current. So the current through 20 ohm resistor is equal to 250 milliamps. This is your answer for this problem. In this problem, they are not given the options, only they have told to calculate the answer. They are given there is no options are given, simply they are given calculate the answer. So the current through your 20 ohm resistor is equal to 250. Next we can move to a next problem. fourth problem. Here also is going to be a rectifier problems. Okay, just we are going to calculate your resistance. Here also given to calculate the values of resistance of your full wave rectifiers. We are going to calculate the resistance of full wave rectifier in terms of ohms. Here also there is no option is given, just we have to calculate the value of your resistance according to your given data. What are the data given means, here the V RMS value is given, is going to be a 230 volt is given, and next it is given is only your 10 amps. This is your average, your DC current is going to be your 10 amps, which is equal to I average current. The average current is equal to your DC current, which is given as your 10 amps, as well as your RMS voltage. VRMS voltage is given as 230. We are going to find the resistance. RMS resistance is equal to VRMS divided by your IRMS. We have to find the value of VRMS divided by IRMS. VRMS value it is given as 230. Now we have to find your IRMS. How we can find your IRMS? Okay, the IRMS value is equal to the formula for calculating your RMS current. IRMS is equal to pi divided by root 2 into root 2 into I average. This is pi is going to be 3.14 to root 2 of 10. If you simplify this, you will get 11.11. So IRMS. So your RMS value is equal to V RMS divided by IRMS is equal to 230 divided by 11.1. We are going to get some 21.7 is your resistance value in terms of ohms. So the final answer of your resistance in terms of RMS is equal to 21.7 ohms for this answer. This is your rectifier applications. And next problem, the final problem, is going to be your clipper as well as your clamper. There is a circuit is given. In the circuit, which waveform is the correct waveform? Which option is going to be the correct waveforms for a given network? We have to identify. Okay, here it is given your diode is connected in shunt. Okay, here a diode is connected in shunt. A resistor is connected. Okay, what is the output voltage? If your capacitor is connected in series with your diode, then this circuit we going to be called as a clamper circuit. But your capacitor is not connected, here a resistance is connected. If the resistance is connected, then this circuit is going to be a clipper circuit. So in this, which one is going to be the waveforms? Already I have told here the biasing is applied. Your input voltage is going to be the 10 volt. V RMS voltage is equal to 10 volt. The biasing voltage, V biasing is equal to 5 volt it is given. If it is a clipper, we are going to remove your unwanted portions. Okay, in that waveforms we have to create. Here the input cycle is going to be your cycle. This is going to be your 10 volt and this is going to be the 10 volt. In that, if you apply your positive biasing, this is your positive negative. If you are applying a positive biasing, we have to remove a 5 volt in your output cycles. You can see here it is your 10 volt. Here it is also 5.7. It is also 5.7. But in your option C, you can check your positive is 5 volt, negative is 5 volt. If it is a clip, your total input voltage is 10, you are going to clip your 5 volt, then your result is going to be the 5 volt is going to be the answer. If your option A, it is given as 5.7 as well as 10. Option B also 10. And option C, you can check it is a 5. So the correct option is going to be the C options. So remaining voltages, everything are not in values. So it is not exactly a 5 volt. 10 minus 5 is equal to 5 volt. This is your input voltage, this is your bias voltage. So remaining voltage is going to be the 5. The option may have a different voltage, option B also different voltage, option D also different voltage. So option C is going to be your right answer. Yes, that's all for my session today. Thank you one and all. We will meet on next session, next video session. Thank you.